Last time we did 47th, right? So 48 now. Where do you go? Okay, 48. Next. A solid body rotates with deceleration about a stationary axis with an angular acceleration. Okay, angular deceleration beta proportional to square root of omega, where omega is angular velocity. Find the what mean angular velocity of the body averaged over the whole time of the rotation. Fine, so just a differential equation. So d omega upon dt, right? So it's going to be omega power negative 1 upon 2 d omega is equal to dt. Wait, what? Yes. Actually, it should be k dt, where k is the proportionality constant over here. So k square root of omega, that would be the thing, right? Okay, then you can just say, okay, omega power 1 upon 2, 2 times of that, that's supposed to be equal to. So initially, what is omega? Oh, it's initially omega naught. So minus 2 omega naught power of 1 upon 2. That is equal to k times t. Cool. Yeah. And what do we need to find? We want to find the mean angular velocity of the body averaged over the whole time of the rotation. Oof. Mean angular velocity. So that would be the complete theta upon time, right? Just not good. Fine. So like 2 square root of omega is equal to 2 square root of omega naught plus kt. And then you can just square this, of course, and then you will get what d theta upon dt is, and then integrating that you will get what theta is. Just a very big way to do that. I don't want that. Oof. Something else, something better than that. So it really is just theta upon t, right? So it's gonna be integration of omega t upon integration of t. Man, you really have to find omega for it. There's no other way to go around this. Anyway, let's just do this. So we'll say 4 omega is equal to 4 omega naught plus k squared t squared plus 4 square root of omega naught times k times t. That should do it. Okay, and then we can integrate this thing. So this is times like 4 theta is equal to, so this is just going to be 4 omega naught t, and then plus k squared upon 3t cubed plus 2 square root of omega naught k t squared. Let's do it. And now what we want is this thing upon t. So we'll just have 4 times average omega, that is 4 omega naught plus k squared t squared upon 3 plus 2 square root of omega naught that times kt. Now good thing is that it's just in terms of kt completely. And what is kt? So oh yeah, so kt is this quantity, so you can find that in terms of omega. And what do you want to find? Right, so they didn't give us what k is supposed to be, so we'll have to eliminate that somehow. The only way to eliminate it is using this equation. That's one thing that we can do, or we can do beta is equal to yeah, beta is equal to k square root of omega, and then right from that you find something. But what about the time? Time will be there all the time, right? So we don't want that. So instead just go with omega, right? Using this equation we can deal with it. This will be 4 omega naught plus kt square of this thing. It will be 4 into square root of omega minus omega naught minus square root of omega naught, that's in squared. So that should be omega plus omega naught minus 2 square root of omega naught omega. Okay, that upon 3, and then plus, so 2 square root of omega naught. Let's see, something cancels out? I don't think so. So you got square root of omega naught times omega, and you got this thing over there. Let's do it. 4 omega naught plus 4/3 omega plus 4/3 omega naught. Over here you got minus 2 omega naught, and then minus 8/3 square root of omega naught omega, and plus 2 square root of omega naught omega. So minus 8/3 plus 2, that is minus 2/3, right? Because I think plus 6, yeah, minus 2/3 of this thing, and then this is not there. Okay, so 4 omega naught plus 2 omega naught is just 2 omega naught. That plus this, that will be 10 upon 3 omega naught 4/3 omega minus 2 square root of all that stuff. Fine. So you can just put that in there. So our answer is average angular velocity. That is this quantity. Sorry, 1/3 of 10 omega naught plus, oh, you can actually also take 2 out of it, so it should in fact be 2/3, and now this will be 5 omega naught and plus 2 omega, okay, minus this 2 is gone, so minus square root of omega naught omega. Is that, yeah, that looks correct. Cool. So this is it. Next question. Yeah, so 48 done. So wait a second. This thing was 48. Go to 49 now. Solid body rotates about a stationary axis so that its angular, angular what? Angular velocity depends on the rotation angle, like this. Okay, where these are positive constants. At the moment t equal to 0, the angle phi is equal to 0. Fine. Time dependence of, fine, so just solve this resolution like d theta upon d, sorry, d phi upon dt, right? So you can say, okay, d phi upon, I don't know, is this supposed to be psi or something? Whatever. Let's just use theta instead. Yes. Upon a minus, sorry, upon omega naught minus a theta, that will be dt. Integrate this thing's natural log of, let's see, omega naught minus a theta, and initially your phi theta whatever, I think is 0, so it's going to be omega naught. Ooh, it's like first degree kinetics, something like that, whatever, right? I mean, the differential equation is the same, but it's not kinetic. I mean, sorry, it's not, yeah, it's not chemistry, it's physics, whatever. Omega naught minus a theta is equal to e power, wait, what? That doesn't look good. It's supposed to be, oh yeah, so when you integrate this, you have to divide by negative a, right? Yes, now it will work. So this should be omega naught, right? Now it makes sense. E power negative 80. There we go. So your, what do you want to find? The rotation angle, first of all. So that will be a theta is equal to omega naught into 1 minus e power negative 80. So you can say, okay, theta is omega naught upon a into 1 minus e power negative 80. So you got a done at least, which is omega naught upon a into 1 minus e power negative 80. Cool. And what else do you want? So b is the angular velocity, just differentiate that in separate times. It's going to be, so negative a comes down, it's supposed to be a is like omega naught e power negative 80. This was just yeah, I mean, you have this equation, so whatever. Let's go to 50. So 50 is a solid body starts rotating about a stationary axis with an angular acceleration beta is equal to b naught cosine phi, where beta naught is a constant vector. Oof. So phi is an angle of rotation from the initial position. Okay, find the angular velocity of the, fine. Wait, what? Angular velocity is a function of theta, phi, whatever. Okay, so it's even easier. So it's just going to be omega d omega upon d theta is equal to, so I use theta, they use something else. Is this phi, psi, whatever that thing is? But I use theta. Don't get confused by that. Cosine theta. Now, yeah, just integrate this thing. So like omega squared upon 2 goes from any initial conditions. No, that's not initial conditions. What? But fine. So just have to go with it. So indefinite integration, it just gives us b naught sine theta, yeah, plus some kind of constant. That should do it. Omega square is equal to 2b naught sine theta plus some constant. Not sine theta plus some constant. So that's square root of that or whatever. That should make sense. Fine. So we want to drop lot of this dependence. Are you serious? This is omega squared, not omega. This won't. Oh, come on. Why? So let's talk about 2b naught sine theta. So that sine theta is 0, it's 0, whatever. But you actually go up by c, whatever c is. So if you want to take square roots, then this should be positive everywhere, or at least in the range of t that we are dealing with. It should be positive. So maybe like this. Yeah, looks like a good sign graph. Okay, this is not. Oh, come on, why are you doing this? Something like that, right? And then you want to take the square root of that. I mean, why? Square root of this thing. So square root of c somewhere over here maybe. And yes, like it will just flatten out it, right? So maybe, yeah, okay, just flatten this out, but keep the same kind of curvature. Something like that. It's still looking something like sine curve, but it's technically square root of sine curve plus some constant. Whatever. I'm just not going to graph this because these in fact look indistinguishable. So not going to graph this. Just put it like that. And this c can be written as omega naught squared, of course. That should do it. Okay, 50 done. Right? Okay, let's put 51. 51 is a rotating disc, moves figure 1.6. Okay, like this. Moves in the positive direction of the x-axis. This is moving in the positive direction of x-axis. Fine. Find the equation yx describing the position of the instantaneous axis of rotation. I mean, oh, so it's like, okay, I understand this. If at the initial moment the axis c of the disk was located at the point O, after which it moved with constant velocity v, while okay. Constant angular acceleration. Oh, come on. Initial angular velocity is. Oh, so the locus of that point, locus of its center of rotation, axis of rotations, its xy intercept. Okay, whatever. Right? Yeah. How do we do that? So let's think about this body rotating. So if this has say v velocity in the x direction, its current position is x, right? So its center of mass position is x. It is rotating with omega in, let's say, counterclockwise direction. So omega like this, it's moving with v, and we need to find where the axis of rotation should be. Can't be that hard, right? So if I basically imagine this to extend out of its boundary, there might be some point over here which is actually not moving at all. So this is moving with v. So with respect to this guy, it should be moving with v in this direction, right? So we can definitely do that. What point will be like that? So if this thing is say r, then you will have r omega is equal to v. So you can find what point that should be. R is equal to v upon omega. Cool. Wait, okay, now I'm thinking, let's use the sine system correctly. So it should be negative v, and call this thing y. So for the general case, we'll take y to be positive. I mean, for just showing how it is, it's not supposed to be positive. And if this is going with, this is what, like y times so j hat, and because this is going counterclockwise, yeah, like this should be v in the it should be negative vi hat or something, and it's too complicated. But hey, you got to think that y times omega, that should give us negative v. Uh-oh. No. No, no, no. It should be positive. Huh. Yeah, it should be positive. Sorry. That figure was just incorrect. This cannot happen. You cannot have V like that. It will be like this. So it has to be positive over here if omega is counterclockwise. And then the sign carries on with clockwise things. So y will be negative in that case or whatever. Because clockwise will be negative. Cool. So you got it. V upon omega. Hey, it wasn't that hard actually. Yeah, it wasn't that hard at all. So now you know what the y coordinate is depending on v and omega. Now, and v and omega, we know the time dependence of these things. And because of that, you also know the time dependence of x. And that's it. You're done basically. So let's go for the first case. This was 51, right? 51 first case is with a constant velocity v, okay? While the disk starts rotating counterclockwise with at 0. Right, initial angular velocity is 0 and constant angular acceleration beta. Then for this thing, it would be v is equal to, sorry, y is equal to v upon beta times t. And of course, x is just v times t, right? So that should make sense. Yeah, looks about right. So this, of course, has x the same thing as this guy's x. So no problem with that. And just multiply these equations. So it's xy is equal to v squared upon beta. So perfect. A done. Xy is equal to you just want y as a function of x. You don't want the locus like in the standard form. So y is equal to v squared upon beta x. That's A for you. Okay, it's supposed to be y. Fine, let's go to b now. So b is where is it? With constant acceleration omega and 0 initial velocity, while the disk rotates counterclockwise with a constant angular velocity omega. Oh, okay, so it's constant acceleration w, sorry. Fine, so it's still doable. So like in this case, v will be w times t, that upon omega. So that's what your y is. And what's your x? It will be, so initially, no initial velocity, right? I mean, that's why it's wt, just half of wt squared. So you can square this thing as well, right? So y squared is equal to w squared t squared upon omega squared. And then what's t squared? T squared is just equal to 2x upon w. So we're gonna put that in there. Y squared is equal to w times 2x upon omega squared. So there we go. This will be y is equal to square root of all that stuff. So square root of 2wx upon omega. Is it charging or something? No, it's not. Fine. So a b done. To the next question. 52. A point A is located on the rim of a wheel of radius r is equal to 0.5, which rolls without slipping along horizontal surface with velocity v is equal to 100 meter per second. Okay. Fine, fine. The modulus and the direction of the angular acceleration of the point A. So the good thing is that because the center of mass is moving with a constant velocity, your acceleration with respect to center of mass is the same thing as acceleration with respect to the ground. So because there's no pseudo forces. Right, so then the modulus and direction of of the acceleration vector of the point A. So it's towards the center of mass at all points. Right. And what's the modulus? It's just omega squared r. Ha. Exactly. So omega is just v. Okay, fine. So it's just going to be v squared upon r in that case. Perfect, huh? Right. So A, it's very easy actually. So so wait, this diagram is not for 1.52, is it? Fine, whatever. So it's v squared upon r and towards center of mass. That should do it. Or let's just call it center, because it's a disk, right? Where it go? It's supposed to be A. Okay, the total distance s traveled by the point A between the two successive moments at which it touches the. Come on, are you serious? This is the kind of question they give to 10th graders. So it is gonna be the circumference. What was this? So the circumference, which. Oh, okay. Wait. You mean the distance traveled by A, not. Oh, okay. This is different. So, this is very different. Sorry. Distance traveled by the center of mass, but by A, that's a completely. So it's like a cycloid motion. Oh no, oh no. This is going to be very complicated. So let's do it. Let's figure this out. So the wheel's center of mass is moving with, say, uh, velocity v. So that will have vt comma 0 as its. So yeah, I will just say that this thing. Okay, no, don't do that. Vt comma r is the coordinates of this thing, and so it's going like what, counterclockwise? No, clockwise, because this is actually going in this direction. So this is moving like that, right? Yeah, so it's gonna be clockwise. Then you can say theta will be equal to negative omega t. I know, looks weird. Why should it be negative? It is, right? It just is. What did they say? Where did it go? Yeah, just velocity is given. You don't. They didn't give us anything about omega, but we know omega is going to be clockwise. Fine. So now we got about theta is, which is of course the angle that it makes with x-axis, right? Okay, you get that. Then right, CA vector. If you don't get that, and then it's just gonna be cis of this thing. So r times cosine of this, cosine omega t, negative sine omega t. That should be the thing, and then this thing times that. Sorry, plus that. Oh god, why is this so complicated? Well, you can write this as r omega, so that's better, right? So it's basically just r times of let's see, omega t plus cosine omega t, and then you got 1 minus sine omega t. This is the coordinates of the point A. So what we want is well, first of all, you would like a y. Wait, what? Oh yeah. Okay, thanks. Yes. Now, right? Is it worth it to find out relation between y and x? Actually, no. The problem is that, yeah, why do that when you already have it parameterized in t, right? So what will be our path? That's just going to be integration of ds, and dx will be just, well, dx square plus dy square, the square root of that thing, right? And it's going to go from, oh, this is going to be bad. Okay, you can write it differently. You can write as dt square root of dx upon dt square plus dy upon dt square, and then you want to integrate this thing. Yes, that will be our distance traveled. That should do it. So dt, but we already know what dx upon dt is. Yeah. Oh no, it's different for these different points. So actually no, you have to fill that out. So dx upon dt, you can take that r out from this thing, and then when you integrate this thing, you're gonna get omega out as well. Cool. Omega r, and now over here just have, well, that omega is gone, just only 1 plus. Okay, so it's cosine, that's my negative sine omega t, right? This thing squared and then plus, so it's actually that thing, but actually it's gonna be negative cosine omega t, that is omega and all that stuff. So omega is out anyway. It's just cosine squared omega t. Cool. So you got what we want to integrate. Oh, it's going to be a long day. Yeah, right. And yeah, it's going to be definite integral. So what is the time period of this thing? Because that's over how much we want to integrate. So let's say initially let's say a is at, oh yeah, it just makes what it makes. omega t angle with the x-axis, isn't that right? So initially your A was on the horizontal line, right? So this might have been your A, and then it's gonna go like this. Fine. So instead, yes, I get that. So what we'll do is that instead we'll wait for it to go down. That will get pi by 2 phase or whatever. So for that you need the time period upon 4. So what's the time period, by the way? Time period will be 2 pi upon omega. That should make sense, right? So 2 pi into that form. Exactly. So 1/4 of that pi upon 2 omega. And then next time this happens, that will be at, oh, it should be negative, but yeah, this was negative anyway, so that would make perfect sense. So then the next time this happens is when it will come full circle. So pi upon 2 omega plus 2 pi upon omega. We're gonna integrate this thing. So omega are out because constants. The integration of this thing. So dt square root of, let's see, you can write this as 1 plus 1, 2 minus of 2 sine omega t, right? Which is, oh, this is going to be really bad. First thing first, take that omega in and just write it as t of omega t, and let omega t equal to, I don't know, u. So it will be r integration from pi upon 4 to pi upon 4 plus 2 pi of du square root of 2 into 1 minus sine u, which is basically just 1 minus of cosine pi by 2 minus u. So that will be 2 sine squared of pi by 4 minus u, I think. Because it's sine squared, we can just write this as u minus pi by 4. It won't make a big difference. Yeah, cool. Now, u minus pi by 4 goes from 0 to 2 pi, and d of u minus pi by 4 is still the same thing. So instead of that, we'll just write it directly like this and cut out these. So this will be from 0 to 2 pi now. Perfect. Now it's just, yeah, we are so close. 0 to 2 pi. Oh no, so 0 to 2 pi. Yeah, you know what? Write this as 0 to pi upon 2, but 4 times. Exactly. And you also got this 2 times 2 is 4, and then yeah, it's gonna be 8. And now it will just be sine u du. Why did I do that? Because it was symmetric from 0 to, I mean, there's a 4 times of this integral. Symmetric everywhere, right? So 0 to pi upon 4, whatever. So sorry, pi upon 2, sorry. 0 to pi upon 2 in the first quadrant, whatever happens, same thing in the second quadrant, same values, that is same thing in the third and fourth quadrant as well, because it's mod. Nice. So this should be our distance, no big deal. So it's just negative cosine u goes from 0 to pi upon 2, it's going to be 1. And there we go. So 8r is the distance. Hey, this is awesome. It's like simple, really simple. It's so much more simple than what I expected this to be. Okay, weird. So for this guy, for the center of mass, this will be 2 pi r, right? But then actually just 8r because wow, awesome. Next question. So 52 done. Let's go to 53. 53 is a ball of radius r is equal to 10 centimeter rolls without slipping down an inclined plane, so that center of mass center moves with constant acceleration. Okay. 2 seconds after beginning of motion, its position what am I saying? Its position corresponds to that shown in the figure 1.7. Right, so it moves down, right? Inclined plane. Yeah. Center moves with constant acceleration. Okay, without slipping. That's nice. 2 seconds after motion, its position corresponds to that shown in the figure. Velocities of the particle A, B, and O, the acceleration of these points. Oh, okay. This is going to be a problematic thing because we will have to do inertia and everything. Let's do it. So first of all, our the main thing I want to find out is what velocity will this actually gain when it after 2 seconds, right? Wow, just whatever, do it. So think about it. You got g sine theta acceleration acting on is actually like force would be mg sine theta, right? About this axis, so this axis is going up from out. I mean, like outside of the plane, right? So about this axis, what's the inertia of this? What's this sphere, right? Right, it's gonna be 2/5 of mr squared. That's for about a diameter, and then plus mr squared. So parallel axis, 7/5 mr squared. So this force times is like r. That thing upon this, and that times r. That will actually be the acceleration. So you can say, okay, acceleration, which they use w for. Man, are you serious? Oh wait, they already told us what acceleration. Huh? Are you serious? So, okay, they didn't give us the mass. We don't even need the mass actually. Wait, why did they give us the acceleration? Because they didn't tell us what gravitation is right now. Of course, I mean, it could be that g is a variable at this point. So you will just have to use this thing and not use this, the normal way. Okay, so acceleration times time, that's the velocity. Cool. It's just 5 centimeter per second. That's how fast that's moving. At that point. Okay, cool. The velocities of the points A, B, and O. This thing is moving with what? 5 meter per second, right? C is moving with that. So A is going to move with 10 meter per second. O is 0. B is, so it's 5 in this direction, 5 in this direction. It's like 5 square root 2, basically. Wait, when you say velocities, do you want in vector form? No, I'm just going to give you the magnitudes. So A is just 10 centimeter per second, right? B is 5 square root 2 centimeter per second. I don't like using centimeter per second, but it's easiest to do it using that right now. And C is of course just that, but we don't want that. O is 0, so looks weird, doesn't it? Okay, B, acceleration of these points. Fine. So yeah, once again the same thing, mv squared upon r in this. Oh no, there's tangential. Okay, this is bad. Good thing that it's just the acceleration. So like you can use pseudo force or something, right? Yes, like with respect to the center of mass, the acceleration is just centripetal. So oh no. There's also tangential acceleration. Okay. There's also tangential acceleration. That's awful. So there's centripetal acceleration, just v squared upon r. Yes, then there's tangential acceleration, which is so d omega upon dt times r. D omega upon dt is like d v upon. Okay, so it's gonna be the acceleration w upon r. That times r, of course. That would make sense, right? So w is the tangential acceleration as viewed from c, but that's along tangent. That's a different thing. Okay, and the thing is that c is moving with w as well, so pseudo force, pseudo acceleration, or whatever. So each point will have, so for example, for a, it will be a radial acceleration like this. So it's omega squared r. Oh, okay, we don't want omega squared r. Just want v squared. So v squared upon r. There will be tangential acceleration, so it's going in clockwise sense in this case. So that's why I like that. It's going to be just w, and there's the pseudo force, so w in that direction. That's it. So like v squared upon r in this, which makes sense considering that this is kind of like a cycloid or something. But wait, what? Oh yeah, of course it makes sense. And what about b? So for example, okay, so for b it will be v squared upon r in this. This is just getting out of hand. First of all, calculate what v squared upon r and all these are. It's like W in this direction and in this direction. Something. Ah, let's do it. Fine. What's V squared upon R? V squared upon R is, what's V first of all? 5 centimeter per second. So 5 centimeters square per second square. That upon R. R is 10 centimeter. So it's 25 upon 10, right? So 2.5 centimeter squared. That's upon centimeter. So centimeter per second square. What's W? So W is once again just 2.5 centimeter per second square. Cool. So let's talk about this one. It's just 2.5. It's like, okay, cool. Do this thing. A. 2.5 centimeter per second squared downwards. What about B? You got, what's this, like 5 in that direction, 2.5 in that direction. Oof. So in total it will be, so like square root of 2 square plus 1 square should be the thing. So square root of 5. Wow. 2.5 square root 5 centimeter per second square in, I don't know what direction. It should be something like that. Whatever. C. So not for C. We want O. For O, right? So it's V square upon R is 0. Is there also centripetal acceleration? Tangential acceleration there is, which is in this direction, and there is also the pseudo force. So that, right? Something doesn't look. Oh no, I messed up everything. Ah, no, no. You don't put pseudo force like this, right? Instead, we already got the acceleration as seen by C, and then we need to go back to the ground frame. So for that, we don't need to add pseudo force in that direction, but the opposite direction. Ah, like we are countering the effect of the pseudo force. That's why it should be actually like this. So what I calculated for B, that will be in fact for A, and let's forget the directions and everything. So for A, it will be this thing. What about B? So for B, it's omega in this direction. This cancels. So it's just omega, sorry, W in that direction, like 2.5 centimeter per second. And for O, it's W in this direction, and there's no, yeah, and then there's tangential accelerations like W in this direction. 0. Cool. Which is to be expected. Cool. Okay, next question. Yeah, I know. Just put it on charging. Okay, let's go to 54. Just wait a second. Right. 54th. 54th is a cylindrical, what? A cylinder rolls without slipping over a horizontal plane. The radius of the cylinder is equal to R. Cylinder rolls on horizontal plane. Radius of cylinder is R. Find the curvature radius of the trajectory resolved by the points A. What? A and B. Wait, what? Okay, so from one point. Uh oh. Right. This is just really bad. Hey, at least we got what the velocities are and what the acceleration is, right? So A is the easier case. What about B? Unfortunately for B, velocity is in this direction and acceleration is so acceleration is downward, right? Because it's this omega down and omega this side and centripetal acceleration this side. So cancels. It's got omega down. Sorry, W down. So for B, what's happening is that it's W down. That's our acceleration basically. And you got 5 square root of centimeter per second in this direction. So basically this angle should be 45 degree, I guess, right? So V squared upon acceleration, in this case it will be this thing, right? It's just that part, which is not that bad actually, because it's just, yeah, right, that thing. So yeah, it's just gonna be 5 squared upon in CGS units upon the acceleration, which is 2.5 in this case. That will be 2 into 5, so 10. So for B it's 10. Hey, nice. Radius is 10 centimeters. The fourth, so P is 10 centimeter, I think. What about A? So what about A, huh? A has 2.5 centimeter per second square acceleration in downward and no. Uh-oh. So A is okay. A is also just that tough. Come on. Okay, this is not how it should. It should be 2.5 square root 5 like that. Uh, uh, so A is velocity. That is in this direction completely, right? So 2v and its acceleration is in some really bad direction because it's got 1 unit over here and then 2 units over here. So this is bad. This angle should be 60 degrees, I think. So then this angle will be 30 degrees, right? So then, okay, we just want this component of it. So this is going to be 60 degrees. So 2v cosine 60 is just v like that. It's v squared upon this acceleration, right? Which we found out. It's supposed to be 2.5 square root 2. So it's square root 5. And v squared is, so A is moving with 10, so it's supposed to be 100. That should do it. It's like 1000 upon 25, so 40 upon square root 5, so 8 into 5 upon square root 5, 8 into square root 5, 8 square root 5 centimeters. No idea how accurate this is. Next question. Two solid bodies rotate about stationary, mutually perpendicular intersecting axis with a constant angular velocities omega 1 and omega 2. Okay. So bodies rotate about stationary, mutually perpendicular intersecting axis. Okay. Find the angular velocity and angular acceleration of one body relative to other. Wait, a whole body is not a reference frame. So what do you mean relative to other? If this was point objects, this would have made perfect sense, but oh, so like, okay, I get it. With respect to the first guy, what's happening is that the whole world is revolving around, okay, this sounds very fine, but you get the idea, right? I mean, this, if this disk is going like this, then according to this, okay, so there's some fly over here which says the disk going like this, and then according to this, actually the fly is going like that, right? Exactly. So yeah, seems like for any rigid body you can still do it, right? Oh, cool. uh, and yeah, in fact, what should happen is that not we won't think about we should think about in the vector form, right? The angular momentum vectors, those, right, subtract those basically. Isn't that what you're saying? Still, it's hard to justify why we do that. I get that all the velocities will be, yes, like there will be omega r component of velocity added all of the time, everywhere. Yes, you can sense that, sure. But then that omega r will be different for each of these different points. That's a problematic thing. Okay. So these are intersecting axes, you say. So maybe like the first body is rotating, okay, just for it like this. This is our first body rotating like that. And then it's some other body rotating like this maybe. Right, this is rotating about that, rotating about this. Okay, cool. So basically like a gyroscope. Thing is, can we directly add the angular momentum? Sorry, subtract the angular momentum, like can we do that? actually. I don't know. Doesn't look correct to me. Angular velocity. Yeah, it's like, for example, if say if this was linear momentum, so a fly is moving with velocity 5 meters per second like this, and then there's a train that's stationary. I don't know, it's very massive. So according to the fly, this has momentum much bigger than what it actually has as we see. Right? I mean, according to us, is zero. Sorry, it has much bigger momentum than what we see of the fly. Maybe this is like 1 gram, and this thing is, I don't know, many kgs. Okay, clearly the momentums are different, right? So maybe we cannot do the same. Yeah, we cannot do the thing with linear momentum. So why do we expect this to happen with angular momentum? We can definitely go for angular velocity. So we can do this thing minus the angular velocity vector. That would make perfect sense, right? Yes. So think about it. With respect to this point, the angular velocity vector of this horizontal body that's going up, cool, and that's like it's the sum of all of these. Uh, how do I tell what this is? It's not like that. It's not like it. Whatever. And for this guy, if this is going omega, then you reverse that. Then what will happen is that just add up the opposite angular velocity vector to this thing. So now it will be like this and that, something like that. So it's going to point in this direction. That should probably make sense. Yeah, I think it does. It does. Because essentially what's happening is that, I know, like, you can't actually think about what's happening because there are two rotation axes, and yeah, but you can think about what's happening to the velocity. So if this thing, if it sees everything else having an extra component of velocity as omega r, then we are basically just doing, so for each of these points on this body, what we are doing is just the velocities, they add up like this. So v1 vector, which was because of the original one, then you got v2 vector. So v1 vector was omega 1 vector times r, I should say cross r cross this thing, and then plus r cross omega 2 vector. So you can do r cross omega 1 vector plus omega 2 vector. That would be perfect. Makes sense, right? So you're just gonna add up these omega vectors and then you will have the thing. Cool. So let's do it. So tell me, what's the omega for these two bodies? Where did it go actually? It's supposed to be 55th. So omega 1 is this, omega 2 is this thing, find the angular velocity and angular. Oh, this is nice values. So 5 will be the final omega vector. So angular velocity, so that's just, yeah, omega final vector is equal to omega 1 vector plus omega 2 vector, sorry, minus omega 2 vector, but you get the idea, right? Hey, is it 2 with respect to 1 or 1 with respect to 2? One body with, okay, but which body? Whatever, does it even matter? Okay, cool. That implies omega final is 5 meter per second, radians per second, sorry. That should do it. I should say omega total, right? That will be a better description. Omega total. And what else do you want? You want angular velocity and angular acceleration of the body. Oh yeah, so like if you can just no, there's no angular acceleration because omega 1 vector doesn't change, omega 2 vector doesn't change with respect to time. So their vector sum also doesn't change. Yeah, that also doesn't change. So angular acceleration is 0. Cool. And angular acceleration is 0. Okay, let's go to 56th. A solid body rotates with angular velocity this. Oh yeah, 2 dimensions. Are you? Ah, okay. A, B are given, then I, J are given. Fine. The modulus of the angular velocity and angular acceleration at the moment t is equal to 10 seconds. Fine. At t equal to 10. First of all, what's the modulus of this angular velocity? Square root of this thing square root. Cool. So take that t out, square root of a squared plus b squared t squared, which is, so at t equal to what, 10 seconds, this will be 10 square root of, what's a is 0 0.5, so 1/4 plus b 0.06. Are you serious? So that times t, that's going to be 0.6, huh? So you can just take 0.1 out. This is so frustrating. Okay, so 10 times 0.1, that's out. Then it just becomes 5 squared plus 6 squared, so that's 25 plus 36 is 61. So sort of that, bad, very bad value. Okay, fine. And what else do you want? You want the angular acceleration in the moment. So angular acceleration as a vector, I think, huh? That would just be equal to a comma 2b times t. That will be good. So at t is equal to what? 10. A times, that's okay, there's no t over there. Fine. So 0 0.5 comma 2 times of 0.6 times of 10, that is 1.2. Therefore magnitude of this thing, that is going to be 1.3, right? Plus 5 squared plus 12 squared plus 13 squared. Should make sense. Okay, and b, oh, this is just a actually. Why is this doing? This thing is a, and yeah, and what else you want? B is the angle between the vectors. Let's minimize some stuff. Okay, let's go for B. Angle between these vectors. So our omega vector is 8t comma, just find it out in general. So bt squared, which is in fact collinear to a comma bt. And then the other vector is collinear to a comma 2 bt. I mean, it is a comma 2 bt. And then want angle between these, so that take a dot product, divide by their magnitudes. That will give us cosine theta. That will be a squared plus 2b squared t squared upon the magnitudes of, yes, like a squared plus b squared. You get the idea. And you already got the magnitude, so that's perfect. Right now, what will this be? So it's 0.5 squared, so like 0.25 plus 2bt squared. So bt is just 0.6. That thing was like 0.36. 0.36 times 2 is 0.72. That upon the magnitudes. So we already got the magnitudes, which is 61 plus, crazy, huh? It's 61. Yeah. Oh, okay. This is not what we are looking for. This 61 is that times speed would give this thing. So this upon 10. Yeah. So it should just be square root of a squared plus bt squared. And that would be 0.25 plus bt. bt is, okay, 0.36. So it's going to be 0.61. Square root of 0.61. Wow. Okay, and then plus square root of 1.3. Cool. This will be, it's like 9 and 7, so 0.97, but actually it should just be 9.7. 9.7 upon square root of 61 plus square root of 130. That would be it. Come on, this is just the worst. So cosine inverse of this value, whatever that is. Oh, sorry. So it's not square root of 13, it's just 13. Oh, yeah. Sorry. It should be just 13 like that, not like that, huh? Okay, now that's good. Looks good, I think so. So there we go. Yeah, that's it. You just have to leave it like that. So the angle will be cosine inverse of this quantity 9.7 so yeah, 9.7 on square root of 61 plus 30. Okay, let's go to 57th now. A round cone with half angle alpha is equal to 30 degrees and the radius of the base r is equal to 5 centimeter rolls uniformly and figure 1.8 you say. Okay, this thing. Okay, without slipping on horizontal plane as shown, the cone apex is hinged at the point O, which is on the same level with the point C. Okay, fine. The cone base center. Okay, sorry. C is the cone base center. Fine. Velocity of C is given. Find the moduli of the vector of the angular velocity of the cone and the angle it forms with the vertical. This is awful. This is awful. Do we have to go with element analysis for this thing? No, that would be just stupid to do. So we know that this C is going in. Yeah, we can do that. Sure. Oh, I don't want to find the center of mass of this cone. That would be so stupid. What should I do? Break it up into a bunch of disks might make sense, right? Sure. You want to find the angular velocity of the cone and the angle it forms with the vertical. So this is going in this direction as well as that direction. This is just okay. I think I've seen a question similar to this, or at least I tried to solve that, right? The bicycle physics one. But this is just the worst because it's a full-fledged cone with mass and everything. One thing on it, how would you solve this? Do you need to, I mean, maybe we can find a center of mass and then what? Then it's going it into a circle. Okay, we can do that. So it's angular velocity about that and then the angular velocity of this cone about it. But how do you find angular velocity of this about the center of mass? Because it's not like a planar object anymore. No, this won't make sense. And you also want to find the angular acceleration of this cone. But I mean, once you have angular velocity, it's no big deal. Hey, okay, angular axis, fine, it's changing. That's the main thing. How do you figure that out? So hey, we know that. So you can kind of think about it like this: if O, with respect to O, this is all of this is happening, right? Yes. Now, what I want to do is okay. Imagine that what's actually happening is that the platform on which this is, it's moving, right? It is moving such that this cone actually stays in the place, but it's rotating about its axis, right? So what I'm thinking is that there's this platform, maybe it's like that, and over here you have this cone. So this cone, it's rotating like this, but what's actually happening is that this platform is rotating, which makes this cone stay in that place, right? That would be perfect, right? Yeah. Okay, then with respect to the platform, what the cone would be doing is that it would be doing exactly what we see right now in figure 1.8, right? It's moving such that it's going forward as well, right? Exactly. Yeah, of course. So you just need to find the angular velocity of the cone like this in when this is like rotating and everything. right, in this frame, and then just add the angular velocity of this platform to that angular velocity, and we will have it. Isn't this just perfect? I think it is actually. Yeah, that probably does make sense. Okay, so let's do it. So all we know is what is where it go. Where did it go actually? 1.7, right? Yes. Velocity of point C is given. Fine. So you just have V upon whatever the radius of the whole platform is. Radius of base is, wait, what's the radius? Oh, so this thing is capital R, you say, and okay, this angle is 30 degrees. That's why you can figure out what that should be. Okay, so we'll just call this thing as, I don't know, L. No, let's just figure that out. This thing is R. What's this angle? It's 30 degrees. Okay, don't use 30, just use alpha right now. So then R cot alpha, that will be this thing. So like R cot alpha over here. That's our omega. Omega in this direction, so it's going up. Okay, so this thing is up, and then plus. Okay, calm down, man. Right, these points have to go back by omega, such that this cone would not move in this frame. Yes. Now, what do we want? This cone's angular velocity. So it's moving like that, huh? I mean, of course, it's just like this is moving about its axis in what velocity? What about this little disk as the base? Yeah, this thing is R. This thing is V. Sorry, this is V, of course, but then this is 0. You could just say that. I mean, okay, you can say, okay, or maybe in this frame, this would be 0 and this would be V. That would make sense. So V upon R, should we think? V upon R, that's the omega, but in this direction. So, no, sorry, the opposite direction. Yes. Now we are ready to do it. So this will be in that direction, of course. Cool. So upward direction, call this in k hat, will be V upon R tan alpha k hat, and this is just R hat basically. So this will be our angular velocity in this frame that we want to find it in, right? The final answer. That's that kind of frame, right? V upon R, it was the angular velocity in this frame where the where the base was moving. When I say base, I mean this platform. Okay, and this is supposed to be V upon R times R hat. Wait, no. Its position is changing. Okay, wait. But in that case, wait, its position is changing, right? But over here you can see it's a kind of constant. Wait, this makes no sense. This makes no sense. It's supposed to be time varying. How can this be R hat? Uh-oh. Oh yeah, it's something like a gyroscope. Oh god, this is shit. Okay, so instead let's go with that center of mass approach. So the center of mass is going like this, and about the center of mass, each of the particles. So let's just think about all of the particles lying on disks. So you got this center of mass is going like that, and then maybe some particle is on the rim of this disk or something. So you know that this disk is rotating. So yeah, it's going like this, and then that will be angular velocity about center of mass, and then this itself is going like that. So you will have to add these up. So maybe this is going like that, and then you will add it up, or this is going like that, and you will add it up. Makes sense, right? Sorry, angular velocity is like that. And this guy's angular velocity upon center of mass, something like that, I guess. I mean, about this, it's just that, and yeah, that should make sense because r cross v, huh? So wait, no, r cross v is going like, wait, how can that be? It's changing everywhere. Uh, but hey, going completely by geometry, you can say that yes, d theta upon dt about this disk. So if I look at the base, for example, then the angle that maybe I paint a red line over here, and I'll just figure out what the angle between this red line and the horizontal is maybe, right? That change of that angle, that is basically what omega with respect to, sorry, about this axis of the cone will be, right? So we'll just have that, yes, that thing is a constant, sure. The vector is changing, but the magnitude is constant. And then you can do that. I know, I should just do it to find the answer, but then I don't find it convincing at some times. So I need to convince myself, yes, it works. Okay, this looks good enough. So no, just scrap this. This isn't good, right? This whole argument, it's very complicated actually. We don't know whether or not we should just take this as r hat or maybe as I hat or something like that, because in that case your omega will be fixed. Not good, huh? Not good. Okay. And now what can we do? Right. So it's just this thing, right? Exactly this thing, but not using this, but instead using this. Because of course, v upon r is what this omega is, and v tan alpha upon r is what that omega is, right? So we don't even need to find what the center of mass is, like where it is, because we are not finding inertia or anything, not finding angular momentum. Exactly. So instead, you just have to pretend that you know the center of mass and then do the calculations, because it doesn't actually come into our calculations at all. So nice, I guess. So that will be the thing. Cool. So there we go. Now, what do you want? Once you have this, you want the vector of the angular velocity of the cone. You got it. This vector. So this is what we'll just write it again. V upon r tan alpha k hat plus. This is a nice problem. In fact, I'll make a good video on this actually. R hat. Okay, so you got what omega should be. Omega vector is equal to this. Okay, scrap all of this. And of course, we could have just used the fact that v is equal to r cross omega, right? But then once again, how do you define what omega is? Right. You can use omega to find v, but how do you define what omega actually is? I don't know. Like angular momentum was so much easier because it's defined like just m r cross v, so you can just do some summations and stuff with it to get things done. What about omega? How is omega defined? Maybe it's defined like, I don't know, just guessing, r cross v upon r squared. So this thing, so r cross this thing, what will that be? That will be, let's see, so r dot v. This is getting weird, isn't it? Exactly. Yeah, it's getting very weird. R cross v minus, so r cross v, so r dot v times r vector minus r dot r is just r squared times v vector, and that thing upon r squared, something like that. It's like r dot v upon r squared times r. I don't know. I'll see if there's some definition like this. I think it should be there, some definition like that. Okay, cool. 57th, done. Oh no, okay, we just want the velocity vector, sorry, angular velocity vector. We didn't actually find the angular acceleration. So the vector of the angular acceleration, we've got that over here. So k hat isn't changing, this will be 0, and then plus v upon r. So dr hat upon dt, what will that be? Oh yeah, so if you got a circle, its r hat is changing like that. Yeah, r hat is changing. Then dr hat is this vector, this small vector, and that upon dt, it's just going to be velocity, right? But scaled down. So yeah, basically our angular velocity. That should be doing it. Right, it's just velocity, velocity vector, but that upon the radius. That should be doing it, I guess. Yeah, that makes perfect sense. So you got it. V hat, sorry, v vector upon r. Now, what will that be? You can't just put this thing over here. That would be so stupid. But you can definitely put this over here. So not the complete thing, but just this, because that's the angular velocity that we are looking for in this particular case. So this times v upon r tan alpha. Oh wait, sorry. It's not okay. By magnitude wise, it is angular velocity, but actually it's not like that. It says just v hat upon r, and when v hat changes all of the time. So sorry, v vector just changes all of the time. V vector upon r, you say. And what? So magnitude wise, it's just omega. You just say it's like v upon r tan alpha, right? But its direction is along t hat, not k hat. Cool, that should be doing it. So our angular acceleration, that will be v squared upon r squared tan alpha times the tangential vector. Yes. Yeah, that should make sense. Okay, let's go to what, 58th. Solid body rotates with constant angular velocity omega naught is equal to 0.5 around a horizontal axis AB. At the moment t equal to 0, the axis AB starts turning about the vertical with constant angular acceleration v naught. It's constant angular velocity about the horizontal axis. Okay, horizontal axis AB. Solid body, maybe like a disc or something. Okay. Constant angular velocity, perfect. At moment equal to 0, the axis AB starts turning about vertical. Oh, seriously, now it's a gyroscope basically. Why are you doing this to me? Starts turning about the vertical, the constant angular acceleration p naught is equal to 0.1 radians per second square. Find the angular velocity and angular acceleration of the body after t is equal to 3.5. This is just now there will be forces and everything. What happens to this guy's angular velocity about this axis? We just don't know, right? Is there a force on it? Is something happening? No, we don't know. This is the worst. It's like a gyroscope. Unless omega in this direction, sure. And then we're trying to change this omega, so there must be some kind of angular acceleration, of course. There is that angular acceleration, sure. But wait a second. If I apply forces like this, then the torque will be like that. So instead, what should happen is that this will actually start moving like this. I mean, that's kind of weird, but that does happen, right? You remember the gyroscopes, basically, they do have this thing, this gravity applying force, and then the normal force applying like that. So the torque is like that, but then its velocity is this this direction. So what actually happens is that it just starts going like this and this and this and this. So instead of going like this, it goes like this. Weird, but that's how it works. Okay. Okay. Now what do I do with it? We don't know anything about like what forces are there or anything. Uh, so now what do we do? Do we assume that this guy's angular velocity just doesn't change about that axis? Its vector, maybe its vector doesn't change. Who knows? That could be one thing. Okay. It says that it rotates with a constant angular velocity about the axis, right? So, okay, we can definitely assume that that might be the case. It's not the initial condition, instead it's the general condition for any t. Maybe that's how it is. So, oh, then it's actually like really easy because all that's happening. So let's go for the top view. So the top view, this is our disk. Its omega is like that, and now it's just changing along this circle, right? Its omega is going around the circle. That's it, right? Because this rod, it is going like that, right? Cool. Vertical with a constant. Constant angular acceleration b naught is equal to 0.1 radians per second squared. Oh, so so it's not. Oh wow, this is really complicated because now it's not a constant angular velocity of the rotation of this rod. Instead, it's an acceleration. Fine, angular velocity is no big deal. We can definitely find that out. But acceleration, that definitely is a big deal. So we'll have to find for any general t what angular velocity will be. So, right, maybe it's going anti-clockwise, I don't know. It's gonna go like this. Call this thing theta, right? So your theta will just be equal to half b naught t square. Okay. And your omega vector, call this thing r hat. This thing is, I don't know, this thing is, let's say I hat, this thing is j hat, this thing is k hat, right? So your omega vector, cap, sorry, that will be omega naught times r hat. Cool. Yeah, which is just omega naught cosine theta plus, so cosine theta I hat plus sine theta j hat. And now it's time to do that, huh? We'll find what the angular acceleration should be. That should be omega naught times derivative of this thing. So like negative sine theta I hat plus cosine theta j hat as expected. And that times d theta upon dt, which is, so it's just going to be b naught times t, huh? That probably does it. So you got omega vector and you also got alpha vector. Cool. What do you want? You want, yeah, so like just angular velocity and angular acceleration. Do you want it in terms of magnitudes or what? It's gonna write it as vectors. So your angular velocity vector is omega naught cosine theta I hat. So what's theta, by the way? It's just cosine of half b naught t squared I hat plus sine of half b naught t squared j hat. Yeah, that's it. And what is angular acceleration is equal to omega naught b naught t times, so negative sine of half b naught t squared I hat plus cosine of half b naught t squared j hat. That should do it. Next question. 59. Oh, there's no 59. 58 was the last one, I think. Fine. And then there's this calculation. So at t equal to 3.5, what should be the thing? Not going to do it. This is it. Then there's rigid body dynamics. Okay, so I'll do that in the next video. See you guys in the next video. Bye.